Okay, so let's look at model-based classification with Gaussian distributions. So let's look at the most general case to start with. So basically, I have k classes, k equals 1, little k equals 1 through capital K classes, and the distribution of the data conditioned on class K, that density rather, is Gaussian with mean vector mk and covariance matrix ck, right? And we know that the map rule can be written as y hat when you see a particular data point is you just maximize over k, and I'm going to write down the logarithmic form of the map rule. Log of the conditional density plus, if they have different priors, it becomes relevant, the prior probability of the kth class, right? That's the form of the map rule. And to sort of simplify it, let's just look at what it looks like for the Gaussian density, right? So the Gaussian density, conditioned on the kth class, you have the exponential here, minus half, x minus the mean, covariance inverse, x minus the mean again, divided by 2 pi to the dimension divided by 2, and the square root of the determinant of the covariance. And so now it's just an exercise in algebraic manipulations to now write down an expression for the log of this, right? So it's just minus half x minus mk transpose ck inverse x minus mk minus d over 2 log 2 pi minus half log of the determinant of the covariance. Right? So that's what it is. And now remember that we are going to look at x as fixed, and that's the data that's given to you, and maximize over k. So any term in this that does not depend on k can be thrown out right away. So this term is obviously independent of the class, and so I can cross it out, right? Okay, so let's write out the other terms, and depending on whether there are special cases or not, we might be able to throw out more of them, right? So in general, it doesn't look like I can throw out anything because everything seems to depend on k. So you have the quadratic term x transpose ck inverse x, which will appear with a minus sign. So let me write that down. Minus half x transpose ck inverse x. Then you'll have a linear term, x transpose ck inverse mk or mk transpose ck inverse x. They're both the same thing because ck is positive definite symmetric, ck inverse is also symmetric, so those terms are transposes of each other and equal to each other, right? So you basically have this term appearing twice, and with two negative signs cancelling out, you basically have mk transpose ck inverse x. That's my linear term. And then I still have another one, which is the mk transpose ck inverse mk, which is a constant term. Again, there are three minus signs appearing here, so this also appears with a negative sign, mk transpose ck inverse mk, and the last term is this log of the determinant term, right? Log determinant of ck, right? So now we can look at a special case first, where more terms can be dropped. That's a very important special case where all the covariances are equal. So the special case equal covariances. So CKs are all equal to C. So let me perhaps duplicate this guy. And here it is again, and now the covariances are all equal. So obviously now we can get rid of a bunch of terms. This term here, since CK no longer depends on K, can be crossed out. This term here can be crossed out. So all we are left with is these terms. This becomes MK transpose C inverse X, and this becomes half MK transpose C inverse MK, right? So the final answer that we have here is that let me change the pen back to blue now, is that the log of the probability of X given Y equals K plus the log of the probability that Y equals K, this thing that we are trying to maximize in the map rule, is equal to, and I'm just going to write this down, some linear transformation of the data, some linear function of the data, plus a bias term. And what is that linear function? We can read it off from there. WK is just CK inverse, sorry, let me erase that, is just my C inverse of MK, and BK is this log of the prior probability minus that signal term, the mean strength term. So now when we go back to the general case, what happens? So let me go back a little bit further up. So now let's go back to the general case where CK can depend on K. So we have to bring back some terms that we deleted. So basically, and of course put the subscript K back on the terms we did keep. So what's the term that I deleted? One of the terms that I deleted was minus half X transpose CK inverse X. So that's a quadratic term. So yes, it's a quadratic term. So now I'll have both linear and quadratic terms. But if I'm willing to consider nonlinear transformations of my data point, then I can think of this quadratic term as being part of a feature vector. So, I mean, I'm leading up to logistic regression in this fashion as a sort of a motivation for it. And I should just note that let's actually use the precision matrix notation. Precision matrix PK is CK inverse. So X transpose CK inverse X is X transpose PKX, and basically that is, what is that? Basically it's XI PK IJ XJ IJ equals 1 through D. So what I mean by quadratic terms is all terms of the form Xi Xj. So if I can create a feature vector phi, which is all the linear terms, x1 through xd, and then all the quadratic terms, x1 squared, x1, x2, all the way to x1, x times xd, and then I do the same thing for x2, x2 squared, x2, x3, etc. If I create a feature vector that's as big as this, then I can actually, you can check that I can actually write log of probability of x given y equals k plus log of the probability y equals k, this is the quantity I'm maximizing, as some new wk transpose phi plus some new bk. And that's going to be our starting point for logistic regression. Basically, we are given a Gaussian model, that's a generative model, and from that we can infer that I can write this log likelihood ratio. I'm going to call this L sub Lk. Why am I calling it Lk? Lk is basically the log of y equals k given x, the posterior probability, log of the posterior probability, plus some constant, which doesn't matter, right? So these are basically the log posteriors, and that's what we maximize when we are doing the map rule, right? That's what this business is. So for the generative model, the LKs are basically a linear function of this feature vector. The feature vector can be simply taken to be equal to x if the covariances are equal under different hypotheses or different classes, and it needs to contain both linear and quadratic terms when the covariances may also be unequal under the different classes in addition to the mean. So that's the generative model, generative Gaussian model, telling you that's what you got to do. In logistic regression, what happens is we'll say, hey, we'll start with the assumption that there is some feature vector given to you, and we can represent these log posteriors as a linear function of that. Now tell me the best linear function that you can find that fits my training data. So we are using this generative model as a motivation to get to a more general model where the feature vector now can be coming as the output of a neural network. It can be something you dream up. It can have all sorts of cubic quantities, things like that, or it can be implicitly specified by a so-called kernel trick. So we'll see all that when we discuss logistic regression. But my main point was to use the Gaussian example, which is important in its own right, but also to sort of get to this point where you have this linear transformation of a feature vector.